So you can download these folders from class website where we're gonna upload this one, and it simply unzip. And here, as you can see, there is a Excel file. It's an Excel file named 3D Beam and some version name, and also some very basic. It's not this one. I will show you very basic manuals, but very intuitive. You can just easily follow. And there is the one very special tools. It's called HighPost. This tool is developed using Java languages, so you need to install Java. Java is can be downloaded freely in every PC. The reason why we need a Java is to show graphic results, similar to conventional CA tools, where you can easily check the geometry of your modeling and the result. It takes some time. Okay, so when you try to open this HighPost, which is a Java program, then you will be asked to download this a Java for Windows, and you just say yes, and then it will install all the necessary files to run any Java programs. It will just take a couple of minutes. If you are really interested in developing Java programming, you can find many websites where you can learn how to program Java. Again, Java is the platform free. Oh man. 이 PC 이게 그 관리하는 사람 어디 있냐? 이게 PC가 다운로드 안 되게끔 돼 있네. 응? PC 관리하시는 분들 그러니까. Well, this PC is not our problem. This PC is especially blocked for installing any other software. That's why we could not install. I didn't know. Well, meanwhile, I like to also show you how to optimize your design variable, which can be defined in your Excel file. For example, let's say you like to optimize a certain variable in your input file, such as this thickness. Well, let's say we don't want, we like to optimize this thickness, or we like to optimize the angle to meet all the design requirements. Well, it is often called the design optimizations. And I like to show you a basic procedures of optimization using Excel tools. For that one, let's say let's define a simple equations, such as let's define a problem saying this is the y and x, and we have some kind of function like that, and we like to minimize this y with a certain ranges. Okay, this is the x L, and this is x u, low and upper ranges. So this is the ranges. And where is the which x will minimize this y? Well, graphically we can see this is the one we like to find. Okay, we like to find, and I will show you how to do it using Excel functions without any programming. Well, in optimizations, I mean, this procedure is very critically important in design of any structures, of course, including composite structures. In general, to optimize these y dependent functions, we have to check at the boundary and also many points. But using these Excel tools, this tool will automatically find this y star, I mean x star. Okay. I'm defining these variables. Actually, the coefficients, I like to define this function using polynomial up to power of 3. And this, just define this much ranges. And here, simply A0, okay, plus A1 times X variable plus A2 times X variable square plus A3 times
지금 문의를 해봤는데 대학원 지원팀에서는 해줄 수가 없고 그 담당 기사분이 오셔야 되는데 그 스케줄을 잡아야 된다.
okay. X variable and third power, okay? And is dx is the incremental value. So this one, I would say this plus this increment, and then just copy and paste. Copy and paste, okay, and then this. And then let's try to plot. Okay, so this is the functions we just generate with these coefficients. As you can see that this is the polynomial, constant, and the linear term, and second power, and third power, and so on. And this one is defined as the x. Now, let's say this one is -1, and this one will be also, not this one. I like to start from -1, no, minus, let's say 10. And then this one positive, and this one negative. A little bit more. Okay, we need to do a little bit more ranges. And then let's increase this value. Okay, now, as I mentioned, we like to find this point. Okay, we like to find this point. I mean, x variable, which x variable would minimize these y functions. That's the what we like to do. Okay. And it is important to define a range of this x. Okay. X, let's say we define as minus 0.5 to let's say 0.5 to 20. Okay. And this is the this is the ranges we like to consider. Okay. For that purpose, we rewrite these equations. The reason I'm showing this graph is to show you how this y varies along the x. Okay. Okay, as you can see that if x is about 13, okay, if x is about 13, there will be a 1100, about 1100. That is the about a minimum value. Okay, and again, the point is that how can we find this value x say optimal value, and this is the y optimal. This kind of optimization problem can be defined in many engineering problems. Say y can be a mass of the total structures or cost or strength ratio. Again, we like to find x. X can be angles, thickness, or here only one variable, but can be multi-variables. Okay. And how can we find this value? That's the problem statement. Now here, in your Excel, I'm sorry, they are all Korean, but in your Excel, there is the options and additional functions, and there is the options you can choose from. And be sure to have, you have all the analysis tools. And this is the one, this is a solutions search functions. And then you will be able to see a menu, but you need to check this button to appear in the menu. Okay, here. Now you can see this tool, menu for developers who are advanced functions. It's not easy to find the menu since it's not my Excel. Okay, 어디냐? I'm sorry, it's not easy for me to find from this Excel. Ai. I don't know why they all block the old programs. Hmm. Okay, I will figure it out. The main point is that we define this one as the design variable, and this is a dependent. And we define this range of this x, and we choose optimization method. 해착기가 아니라 이거 누구 써본 학생 없나? 이름이 기억이 해착기가 아니라 개발 도구에 안 나오고 저 백이 뭐냐? 해착기가 이게 어디 있어? Well, I will figure it out, okay, a little later. So I'll just, and then I will download these tools, 3D Beam. And since I cannot do it now, I will just, actually, I was gonna come to these sections, optimizations. So I will go ahead to define this typical optimization problem in composite structures, okay? But what I like to emphasize is that you can optimize the composite structures, a plate, angles, and thickness using your Excel together with using Excel functions. And again, typical optimization formulation for composites, and optimization formulation and understanding concept of optimization is very important for designers. And there are always three concepts. first is the design variables. Define design variables. What you like to find, okay, design variables. So in your Excel tool, design variable can be a thickness of each ply or angle of each ply. That can be a design variable, and subject to certain conditions, which means that, let's say we don't want any ply, we don't want any failure of the any ply. So strength ratio of each ply should be less than 1. That can be a constraint. And if you like to have some constraint on the mass or cost, can be a conditions. And now objective functions. Objective function which you like to either minimize or maximize using this design variable and subject to these conditions. Okay. So one typical case is this one. And optimizations is subject to this condition. Very typical one, as I mentioned, can be a strength ratio. Okay, and objective function is a mass or cost. And this one is a composite pressure vessel, which we already handled several times, and also are covered in your homework. And say this is the pressure vessels under pressure inside the inner pressures, and this any surface of this pressure vessel will be subject to N1, N2. Well, I often use X and Y, but in our notation it should be N1 and N2. And this is a structurally deterministic problem, which means that this Nx and Ny can be determined from internal pressures which are given using equilibrium equations. Equilibrium equation says Nx, okay, Nx times all the lengths will be 2 pi r equal, this is all the forces, and the left hand side there will be a internal axial forces due to pressures, which will be P pressure times a area, so pi r square. So from this we can see that this is the result. Axial in-plane load in the pressure vessel given by pressure and radius and divided by 2. Okay. And another one is the y-directional in-plane load, y directions. And to calculate this one, we just cut in half. We had these pressure vessels, inner pressures, inner pressure like that, and everywhere the Ny will be the same, uniform. So we just cut arbitrarily any sections, and then there will be a Ny in these directions, and this upper direction, there will be a load due to this P. So this length will be a twice of R. So, and this is Ny. So twice of Ny equal twice of R. This is just a projections, will be just 2 times of R and pressures. Okay, this is just projection. Projection means that in each section, the pressure is always a perpendicular to a surface, but the force we like to find is the component in the vertical component, this one, right? And this one also we like to have this and that, and through some mathematical procedures, the result will be simply twice of R, which is the length of this, and times P will be the vertical total force due to these pressures, no matter how geometry it is. So this is the twice of RP, and we have a twice of NR. So we simply say can say that NY is a pressure times R, and NX is the pressure R divided by 2. Okay, so I said this is a deterministic or statically determinate problem. So I will say SD problem. What it means is that internal NX and NY can be determined from just equilibrium equations. There is no material property, no layup sequence here. Just internal pressures can be determined from equilibrium. Equilibrium means that statically equilibrium. So this is that's why we can directly calculate the NX and NY regardless of these all the material properties. Either this can be a steel or aluminum or composite, no matter what the materials are, the NX and NY should be given like that. Now again, the point is that what will be the, let's say this is all angle ply laminate, and we like to define the thickness and theta. This will be a design variable. As you know, you already done this one in your homework, but I like to demonstrate how to do it using Excel optimization tools. So this is the design variables, thickness and theta. And then you can say subject to or constraint will be R, strength ratio of each ply, theta or minor theta should be less than 1. And then we can minimize the thickness. Okay. In general, this objective is a function of a design variable. In here, it happened to be that this objective is just a function of one design variable, which is a thickness. And of course, this constraint R, okay, constraint R is the, I will just say T here, function of T and theta, and which should be less than 1. Okay, so as you can see that to use optimization procedures, it's important to define, we call formulation of optimizations, okay? Formulate optimization. So define design variable, what are the constraints, what is the objective? Objective can be either minimize or maximize. It's not a big problem. So this is a typical problem, which I was gonna show you using Excel, okay? In your homework, what you did was that you plot R, a function of a theta, and you get this this value, and this is the theta optimal value, which was 55 degree, right? Okay, this is the one typical optimization problem in composite structures. Another important subject is the micromechanics. Micromechanics, as I mentioned, we start with applied properties, right? We start with applied properties. Applied properties, we had two groups. One is the stiffness, and the other one is the strength. And stiffness, we had EX, EY, and Poisson's ratio mu, and ES. That's a stiffness related property, and strength is the what? X and X prime, and Y prime, and S. This is all applied level properties, right? Applied level properties. But as you can see that this applied level property is affected by the fiber and resin and fiber volume fractions. So goal of this micromechanics is that, say we have a fiber property and resin property and fiber volume fractions, and how can we determine these ply, stiffness, and strength? That is basically fundamental steps to calculate these apply stiffness and strength using micromechanics. Sometimes it's called homogenizations. We assume that all the fibers are smeared into a resin, and this composite ply become very homogeneous. We don't differentiate between the fiber and resin, and this is the ply properties, right? And of course, it is the anisotropy. Well, I will change a little bit of the order of my class, okay? Because we have some problem with installing some tools, and I was gonna cover the Excel optimizations and introducing this 3D beam, but I will cover this micromechanics first, and then I will get back to that subject. But as you can see that all our chapters, this micromechanics is the almost the last one. Okay? This micromechanics is the last subject. Okay, this is again the another explanations of what I just explained. Fiber plus and matrix, fiber with the fiber volume fractions, and matrix with the matrix volume fractions will constitute composite stiffness and strength. Also, another property, thermal property, is the thermal expansion, coefficient of the thermal expansion, alpha and alpha y. And these fiber volume fractions is very important numbers. And of course, this is the fractions, okay? Fractions, meaning that the sum of these fiber volume fractions and matrix volume fractions should be 1. And sometimes there is a void. Say we have all the composites, fibers, like that. But sometimes there is a little bit of a void. void could be some range of less than 1% or sometimes 2%. And depending on the manufacturing process, such as infusions, would give us the lower fiber volume fractions, but some high advanced, such as the pre-preg, give us the very high volume fractions, such as the 70 fiber volume fractions. But there could be always some void content, which may be important. Actually, this void content does not quite directly affect this composite stiffness and CTE, but it could affect the strength, because the void, let's say this under transverse load, for example, and all the cracks can initiate at the void. Okay, so this small presence of a void could lower the strength significantly, sometimes 10 or 20%, especially this Y, okay, and this S. This Y and S could be easily affected by this void content. But again, stiffness and CTE, while this void content does not affect much stiffness and CTE. The reason is that stiffness is basically average response, right? This stiffness or this stiffness, all average sense. Average response of the fibers and resin, okay, that give us the stiffness. But strength is always start at the maximum stress. So you cannot just average the strength, which is very important in composite structures. Okay, so there are several ways to find. Way means several ways means how do we find these properties from fiber and matrix properties, effective material properties. We could use the FAM, we could use some exact solutions, and we could use just a simple rule of mixtures. So we start with fiber property and resin property, okay? Fiber can also have a stiffness. And resin also can have a stiffness. And fiber has a strength, and resin has also strength. And of course, the CTE and fiber volume fractions, and they are all combined and giving us the composite properties. Okay, here is the real cross sections of the composite fibers and composite materials. Again, like to clarify where it comes from. Say we have a composite laminate. We have several layers. Say this is the 1 millimeters and 8 plies. Okay, 8 plies. And each one will have a different an angle and so on. And let's pick the just one. And it has all the fibers, and this is the figures. Okay, and say one ply. This is the 8 ply makes 1 millimeters. Then 1 ply, how thick is that? Well, this thickness will be 0.125 millimeters. 0.125 millimeters, and which is the about 125 micrometers. And then considering fiber diameters, okay, these fiber diameters is about what? For the carbon, we have about 7 micrometers. So the fibers, if they are stacked them one by one, then about say this is the 125 micrometers, and this is the about the 7 micrometers. And how many fibers do you need? About 15, considering some gaps. Say we about 15 layers, 15 fiber, okay, stacks. So I like to, give you some idea about this thickness and fiber arrangement. So this one is a microscope view, and each one, again, as I mentioned, is a fiber, and they can be some resin-rich area, as you can see here, and sometimes some area has very high fiber volume fractions. Okay, and average-wise, the fiber volume fractions can be ranging from 0.4, 40%, and up to 70%. 70% is like a pre-preg, autoclave pre-preg, and 40% will be some infusions or some, well, these days infusion process will give us also very high fiber volume fraction, but depending on this manufacturing process, we have a different fiber volume fraction, even though we have the same resin, same fibers, but again, depending on the manufacturing process, we will have a different fiber volume fractions. So don't think that, oh, we have a same fiber, same matrix, we'll have a same ply property. Well, that is not true. Certainly depending on the fiber volume manufacturing process. Okay, so when you design as a designer for composite structures, of course you just use the ply property, but you need to know what kind of manufacturing process will give us that ply properties. Okay, that is very important to know. And so design is pretty much combined with the manufacturing process and also a cost. Manufacturing process will incur some cost, and material will also give us some material cost. Okay, so again, the purpose of this micromechanics is that given fiber matrix or resin property and fiber volume fraction, how can we predict ply properties? Okay, ply properties. So this is the purely random fiber. I will call it random fiber, but for the purpose of simplifications and for the purpose of developing unicell, we assume that all the fibers are regularly arrayed. Okay, regularly arrayed, and one is the square array, and the other one is the hexagonal array. And in square array, we assume the fibers are a line like this, okay, only 0-90 directions. And hexagonal array, we can see that this is the 0 and this and this way. So 60, 60, 60 degree. This is a hexagonal array. So this is the real one, but for the purpose of developing micromechanics, we may assume this way or we may assume this way, okay? To calculate the effective stiffness and strength, okay? So, and in scale, as you can see, this is the unicell, okay? This is the unicell. Unicell means that a representative volume which will just repeatedly consist this fiber arrangements. Okay, so so important that is important to consider. We can consider only these regions. Okay, but when we consider this one, so important to note that this is the and that whatever deformation will have to have the same deformation. So this one and that we call repeating boundary conditions. Because imagine that it has these deformations, and whatever happens in here will happen here, because this surface or boundary will be the same as here, because each fiber will repeatedly exist, right? So that's why this is the unicell, okay? Again, unicell is not just free boundary condition or arbitrary boundary condition. Unicell has to meet these repeating boundary conditions. And here, hexagonal, to have this kind of a unicell, we can have different types of unicell, but typical one is that these fibers, and here, this can be a unicell for the hexagonal sequence. Either using scale or hexagonal, the ply property EX, EY, and mu X and ES, this kind of stiffness property is pretty much the same. Okay, you can use either scale or hexagonal. This stiffness is pretty much the same. Of course, you have to have the same VF. This is the VF, fiber volume fractions, and here you have to have a same VF or same VF. Okay, no matter what kind of unicell you are using to develop, to calculate these ply properties, you have to have the same fiber volume fractions. This is a starting point of micromechanics. as you can see, this is exactly what I mentioned, and this one is a real cross sections, and this is a square, and this is a hexagonal array, and we have a unicell. Actually, this is from Wikipedia, and I'm sure this picture is from our lab. But anyhow, so you can, if you, not only just, long continuous fiber, but you can have some particles, okay? Composite can consist of not only long fiber, but some particle like that. And you can also construct a unicell, representative volume element, and many approach. And if we consider woven, not like continuous, woven or braiding has a certain fiber architectures. So we have to model the fiber architectures like that. And each fiber, this is the one toe, and toe consists of a unicells. Okay, you can see there are a lot of research going on in micromechanics, and this is the braiding structures with the all fiber bundle. And this one also can be considered as a unicell, and this one toe consists of a lot of a toe, I mean the fibers, and which is the unicell. Okay, so you can see there are two steps. There are two steps of micromechanics for the woven. This is the either woven or braiding, and structures like that. It could be a biaxial or a triaxial, and here to get effective stiffness, we first define a unicell. As you can see here, this is the one unicell, and this one, either this one or that one, it has, let me magnify here, it has a lot of fibers, and this can be considered as the same configuration as one ply. So this will have a unicell. Okay, so from here to there we call mesomechanics, and from here to there we call micromechanics. If we are working on only unidirectional prepreg type ply, then we only need a micromechanics. We don't need any model for fiber undulations or toe undulations, but for the woven or braiding structures, we have this kind of fiber toe undulations. Another one will be a NCF, non-crimp fabrics. Non-crimp fabrics is the one we have this certain angle, and the other one will be a certain angle, and then here is a stitch. So if we look at this one, we have a slight, we call fisheye. I'm sure we can find some figures. Okay, this is the NCF. NCF means that each ply, okay, this is a dry fabric, okay, no resin, just dry. We have a certain angles, just stack them, and to hold them together, what do you need? What do? We do a needle and stitching them together, and put them into it's called non-crimp fabrics, and as you can see here, its material property-wise is much higher than wovens, but still there is a little bit of an in-plane. Okay, as you can see that this one you have an out of plane undulation. Out of plane undulation is this is a z directions, and out of plane means that in undulation in z directions. And here, so this can be very weak under compression. That is the very significant drawbacks of this woven or braiding. Very weak under compressions, okay? Because these toes can easily buckle, and which will lower the compressive strength. Tension is okay. Tension is not exactly same as a pre-preg type, but say within 5%, that is okay. But compression can be reduced up to 20 or even 30% compressive strength, which is not so good. And for the NCF, little bit stories are different because this fiber runs this way or run that way and then stitch. So there is no out. This is the out of plane undulation, and there is no out of plane undulation. But this one can, when we stitch, this one will have a stitch, and toe will opens up like that. So we would have a in plane undulations. This is out of plane undulations. So I'll just say tension property. Tension property, what I mean tension property is the strength, okay, and compression strength. And if we make a table, say this is the 100%, this is a 100%, the woven tension property will be something 90 to 95. Of course, woven to compare with the UD, you need to consider 0.90, right? And NCF, I would say 95%, above 95%. But the compressive, this can be woven, can be 80% or 80 to even 70%, and NCF will be about 80, 90 to 80% reduction. So you can see that these kind of undulations, toe undulations, will lower the compressive strength. And for example, when you like to have this kind of a pipe, okay, and as a structures, and almost every structure would subject to some kind of bending, okay, and bending and top is okay, is always under tension, but the bottom one is the one under compressions. So almost all structures fail under compressions. But ironically, when we evaluate or compare all the composite property or even steel or aluminum, we always consider tension, stiffness, and strength, right? But in real structures, most of the failure will occur under compression. That we have to keep that in mind. Anyhow, by the way, this tension property and compression strength-wise, this one I would say, if this is a 100%, this will be compressive strength will be lower than tension property, of course. But this is the from my experience. So anyhow, like to emphasize what is the mesomechanics and micromechanics. But I don't want to cover this mesomechanics where we consider all the fiber undulations, but let's say we consider only micromechanics. Micromechanics, as I mentioned here, there could be three different ways. One is the FEM. What is the FEM? Well, we start with this a unicell model, fibers and resin, and given fiber volume fraction, we can easily construct this unicell models. And then we apply certain load here. We will get the very complicated stress distributions and so on. And here we get the EY and Y properties, okay, for the given fiber property and resin properties. This is the AFEM. And again, here and there, we have to consider repeating boundary conditions, so that this unicell is just not the one cell. This would represent a multiply arrayed arrangement. Exact solution, what it means? Well, I don't think it's possible to drive the analytic solution. I would say a analytical solution. Analytical solution with some assumptions. And here, I like to show you what I meant by the okay, this is one typical one. This is a front view. As I mentioned, there was a fiber here, and then on the tension transverse direction, and you can see how this stress distributes. It's not the uniform. It's not easy distributions, and Okay, well, so in here, the procedure I will go through is the rural mixture. Okay, that is the what I like to use, but we can have a choice for micromechanics is a final element method, which I just show you, and analytical derivations or a rule of mixture. What is the rule of mixtures? Well, mixture means a mixture of fiber and resin, and there are certain simple rules. So this is a very easy to follow and easy to program and accurate enough to be used as a design tools. Okay, so not only stiffness, there will be a density. I will start with the density, and let's have a 10-minute break. Wake up. So this is the a Java tool. Okay, as I show you, you download the older tools, develop tools, and when you run it, it will ask you to install Java, and you can easily install. And this is the a result from the Excel. I will get back to this one. I just let you know that the program is well installed. And another one, this is the Excel optimizations. And I just found that there is the menu. I'm sorry, it's a Korean. I'm not used to it. But there is the call solver. You can click there. Then you can define the objective. This is objective, minimize, design variable, and constraint. Okay, you can have several constraints, and you can have many multiple design variables, and this is the objective which you like to minimize or maximize. But I'm not sure. There was always the some error because it is blocked. Yeah. So anyhow, after this run, and there will be a value will be found, and which will minimize this variable. Okay, that's the one I like to show you. Okay, let's get back to here. Density. Well, what is the density? Find. Okay. Density가 어디였지? Okay, so to get the ply properties, now we don't have to worry about all the random arrangement, and we don't need to worry about the all regularly array. All we need to do is just focusing on one unit cell. Okay, one unit cell. This is a fiber, and this is a matrix. And now, what is the density of a composite? Okay, ply. Very simple procedures. And density, by definition, is the volume for mass per volume, right? Mass per volume, that is the density. And what is the mass of this total unit cell? Now this unit cell will represent the whole ply, okay? So the mass will be density of a fiber times volume. So this will be the, we would have, this is the raw fiber and volume. This is not the volume fraction, this is a real volume of this much, such as the volume is like pi r square, r is this one. So this is a volume, and this is the density of the mass matrix, and volume Vm. So Vm can be, say this is the A, and A square minus Vf. That is the volume of this mass, I mean the matrix or resin. So Vf plus Vm is simply A square, is a total a cross sections. Of course, the Z extraction length, we just consider unit length. Okay. So total Vf and Vm equal V. This is the AV, V A times A. And from this, we have a rho F, and Vf divided by total volume. This is, by the way, this is the total volume, which is in this case A square. And we can have a separate terms, and rho M and Vm divided by V. Now, by definition, Vf is a real volume divided by total volume. This is the volume fractions, fiber volume fractions. And this is the fiber in the resin volume fractions. So the V as a ply or composite, I will just say C stands for composite. And composite density will be given as the fiber density times of the volume fractions, and rho M times of Vm. Vm, you can use the 1 minus Vm. Okay, this is the very simple procedures, and this is the rule of mixture. So rule of mixture is just linear functions, and graphically you can say that this is a rho C, and this is the, I will call Vf is from 0 to 1. Okay, 0 to 1. 0 means no fiber, so start with rho n, and 1 you have a rho f and proportional to a Vf, where this is 1 minus Vf, so will be will vary like that. Again, at the 0 and 1, you will have a rho m and rho f respectively, and so this is the again rule of mixtures. Okay, rule of mixtures. Later, you can see that instead of a rho c, you would have a ex. Okay, fiber directional longitudinal stiffness will follow a similar patterns, but this is the derivation procedures. Now the stiffness, ply stiffness or composite stiffness, and longitudinal Young's modulus EX. Well, in your Excel, the database start with these ply properties. Longitudinal Young's modulus EX. Okay, this one we assume very simple a fiber arrangement. Okay, rather than just circular cross sections, we just use a layer, fiber layer, and fiber layers. So this one, you can see that, you know, rather than just, you know, fiber and fiber, something like that, we just simplify this fiber arrangement like that. I'm sorry, this is not the right one. This is X direction, so we can say that here, X direction, we have to have a fiber here. So in this one and that one, and this fiber and resin arrangement is assumed to be just, you know, layered between the resin matrix and fiber and matrix and fiber. Okay, this is the simplest model of the fiber within ply. And then by definitions of this Young's modulus EX, extractional properties, and we first need to define the total force in extractions, total force Fx, and we have to consider A. A is these cross sections, total cross section. A times sigma x. Sigma x is x directional on axis stiff stress, and that should be same as the fiber directional stress and times fiber cross sections and matrix stresses and matrix area. Okay. So if we okay, I will use a different color. In under this load, okay, under this load, what it happens is that the stress-wise, this one, the strain will be the uniform, right? Strain will be the uniform, and that is the about the amount of the EX. Okay, this is the EX. Of course, if we consider this is the length, Lx, we have to multiply Lx. That is the delta X. But point is that strain-wise, the strain is pretty much uniform. Within fiber and resin, doesn't matter, the EX is a uniform. But the stress distribution, it will be quite different. Is stress, the strain is this much, but the stiffness is different, and this will be very high, low, and high, low. This is the stiffness, I mean the stress. Okay, the point is that the strain is uniform in extractions, but the stress will differ between fiber and resin because we have a EX fiber and E matrix, they are different. we multiply the same EX, then even though this is the same, the stress will be different. Anyhow, here, ply level, we don't consider variations of this fiber and resin property. We just assume this is the what? Sigma X, ply stress. So this is the ply stress times the total area, which comes from the fiber stress and cross sections and matrix and cross sections. Okay, so we divide by A, and sigma X is simply, this is the fiber stress and matrix stress, and now this one will be a fiber volume fractions, and this one will be a matrix volume fractions. Okay, so these derivations and results will be different for the case by case, because this is the x-directional property. X-direction means fiber directional stiffness. In this case, the stress, ply stress, and all the strain will be uniform, but the fiber stress and the ply stress will consist of fiber stress and matrix stress. Okay, and then this stress will be a stiffness of a fiber and strains of a fiber, and this one is matrix stiffness and matrix strain. But again, this guy will be the same as the X. That is very simple, but the most fundamental assumptions, and not the assumption, this is the what this ply has to deform. You know, ply and the fiber and resin, they have to deform together. So we put this into here, and this one, and sigma X will be, okay, so this one, and put it here, and then we will, you can see that fiber volume fractions and matrix of volume fractions, and then EF, EM, and there is this and that is the same as EX, is a ply stiffness. So by definition, sigma X equal EX epsilon X. So EX is this much, and so EX is the simply define and follow the rule of mixtures. Okay, fiber volume fractions and fiber stiffness and so on, which is exactly same as a previous one. Well, this is not quite advanced procedures or method, but it's important to understand this the fiber and resin and behavior. And in reality, this EF and EM, well, this one is much larger than EM, and VF and VM is about the same order, so which will be a VF times EF. Okay, so simply we have a fiber property, say 250 gigapascal of a carbon fiber. Then fiber volume fraction is the say 60%. Then you can say which is about 150 gigapascal in x-directional stiffness. Okay, this is a good enough and accurate enough. But again, this one doesn't tell us anything about the how much stress this is the stiffness. Okay? Now, transverse Young's modulus. transverse. Transverse fiber and the perpendicular to a fiber directions. Again, we use these simple geometric assumptions, and now actually this is the y. Okay, this is the y, and we say we have all the fibers arranging this way. And this is the x directions and y direction. And this is a z direction, which is not our concern, x and y. Now, how do we estimate y directional stiffness, EY, okay, EY, and using an EY? Well, first, let's assume how much the deformations, ply stiffness, ply strain, okay? This one, say, it didn't say much here, but let's say this is the L fiber, and this is the L resin, just a length, okay, length. And then this total a delta y, okay, delta y will be, first there will be a strain, fiber strain times LF plus matrix strain times LM, right? This delta will be a result of this fiber deformation and matrix deformations. And let's say we have a total length L. If we divide by L and L, okay? So this one, what is this? Well, this is a definition of the y-directional strain. And then this one and that one is nothing but fiber volume fractions and matrix volume fractions. Okay, so this is the one we got. And for the stress, since we assuming a layered array between the fiber and resin, all the stress here will be the same as the resin. So the fiber stiffness, fiber stress, and fiber matrix stress, they are same. We can say that, okay? This is the same, stress is the same, but strain follow the rule of mixtures. Compared to longitudinal directions, strains are same and stress follow rule of mixtures. And this one comes from the equilibrium equations, and this one, under contrary to a previous one, strain follow the rule of mixtures and stress remain uniform within fiber matrix, and that will be applied stress. And then combining them, say this guy is the what? Sigma EYF will be EF sigma F, right? And same here. So if we consider these conditions, all comes here uniform terms, and we get these equations, right? I can rewrite, and EYM will be a matrix, and sigma M. We put this equation to here, And considering this one and that is the same as sigma y, and we get this one, right? Okay, so, and by definition of EY and EY, we have a definitions of like that. And so you can see that this is the 1 over EY. 1 over EY is this one. So this is the one. A simple equations which we can use to calculate EY using fiber and matrix property. Of course, the fiber volume fractions. Okay, and this one is the linear term, and this is the inversely linear. It's like a spring in series, and this is a spring in parallel, meaning that we have a multiple spring. So this is the something like that, and this one is something like spring fiber, spring mass, and this is the sigma. So in this case, effective stiffness of a spring will follow the inverse rule. Okay, so these are two very simple but very important concept in calculation of ply property using the fiber and resin property using micromechanics. Now, shear modulus, well, we use the same models, and now we applying the sigma x, and we will have a epsilon s, shear stiffness, okay? Shear stiffness, we will have these deformations and something like that, okay? And here we divide each fiber. Okay. Fiber and, I'm sorry, resin and fiber. And we have all the shear stress. Shear stress will be like that, and that, and that, and that, and that, and this, and so this sigma s will apply to a sigma fiber s, okay, fiber s, sigma, sorry, this is a matrix. Matrix and fiber s, they are all same as the ply property, ply stress. So the fiber stress and matrix stress is the same as the ply stress. And then this one, this will have a deformations of like that. And fiber will have a shear deformations like that. So we have a average wise, we consider pretty much the same as a previous one. This is the length and this is the length. So we calculate this angle and linear them. And so the ply shear strain will follow these rural mixtures and fiber, resin, and fiber volume fractions. And exactly same as here. Exactly same, and skip the detailed procedures, and the shear stiffness of a ply will follow these inverse rural mixtures. Okay, this is a fiber and resin. And again, the good thing, a good point of this micromechanics is as long as you have a fiber properties, and now you can change the fiber volume fraction effect, and depending on the manufacturing process, say pre-preg 70% and infusions and 40 or 50%. Okay, so you can easily calculate effective ply stiffness considering all the manufacturing process. Okay, so this is a shear modulus, and there is another step to calculate the Poisson's effect. We follow the very similar step as before, and this is the one where there could be another terms, but we drop other terms, and this ply Poisson's ratio will follow the raw mixtures. And this is the fiber and resin Poisson's ratio. And now CTE, just keep that in mind that we follow constitutivations of the fiber. This is the constitutification for the fiber, and this is the constitutification. Constitutification means that stress-strain thermal terms and stress-strain thermal term for the resin. We just use these terms, and x-directional wise, we follow the raw mixtures. Of course, we have a same EX. So a little bit of a mathematical procedures, we come up with these relations, okay, which is very important. And Y directions, well, a little bit more complicated, but procedure-wise exactly same. And the this is the final terms, and this is the, of course, this is the y directional fiber. I mean the CTE. This is all Y directions, and this is the Poisson's effect. Okay, so everything is clear. Oh, by the way, this is the EX of the previously. We already have this EX. Okay, this EX has to be here. Now, this procedure is important because you have to program that. The strengths, that was all the strengths, and the stiffness and CTE. Now we have a strengths, and strengths we have a, okay, 10 minutes more to go, okay. Longitudinal tensile strengths, okay, as indicated as X. What is X? Well, the stress plus stress will consist of fiber and resin, and then let's say a fiber fails, and x-directional strain of a fiber will be, so epsilon x and epsilon xf will be the same, and epsilon x and m. So this one is the fiber, and this is a resin, and basically this is the EX and sigma x, right? And so X, okay, X comes from here. This one, fiber strength, and for the resin stress can be approximated by this equation, put it here, and then this is the XF. So we can say like that, but again, this is can be simplified as the fiber strength and times of fiber volume fraction. The procedure is simple and result is simple, but we conceptually very important. Stress strain curve of the composite and failure. This is the extractions, okay, extractions, and this is the what's happening in reality. Now, in the fiber, okay, the fiber would have deformed like that, and also matrix will deform, will follow this stress strain curve. And of course, this is the composite stiffness, and this is the fiber stiffness, and this is the matrix stiffness. An important point is that this one has all the same strain, X. So this is the composite. This is a fiber and resin. And all this procedure can be represented using this schematic diagram. And this one is easy to follow, but good to understand the composite behavior. Okay, in extractional, we have a same strain. Okay, same strain. So these strengths I will call X, and this is the fiber strength, XF, but this is the one we can have the relation. You have a little bit of a drop, how much? By fiber volume fraction wise. Okay, this is the strength in extractions. And now, how about the transverse strength? Well, transverse strength in this direction, or using this simple model, just a layered one. As you can see, what makes it complicated here is that all the stress is not the uniform inside, not only in the resin, but also fiber. Stress control is very complicated, and always the failure occur at the maximum point. Where is the maximum point? We don't know. The maximum point will depending on the fiber property, resin property, and fiber volume fractions. So each time we have to go back to final element program and get all the stress control. But once the failure occur, the material property will degrade and the stress will redistribute. So it is not just uniform, it has a progressive behavior, and which makes very complicated. But we are engineer, we like to simplify without losing much accuracy. And one of the very effective way is to assume, oh, matrix stress and fiber stress, we assume some partitioning factor. Previously, we just assumed that, oh, will be all the same, right? All the same. We just assume because this is just a parallel array or a series array. But again, due to this complicated stress distribution, this is no longer true, especially for strengths. So rather than these simple assumptions, we start with these assumptions, which call stress partitioning factor. The value will be like 0.5 or some 0.5 up to 0.7, depending on the material property, but pretty much same regardless of all the material properties and fiber volume fractions. So it's good to use this one. And then this rule of mixture is still valid. So we put it here and we can get, this is the, some concentration factors. So to make long story short, this is the Y directional strength, and this is the XM. This is the pure resin strength, and this is the stress of partitioning factors, and KY is the some concentration factors. That I mean, this can be just used the one. We already have these stress of partitioning factors. Okay, so in your program, I recommend you to use just these equations, neglecting this one. But at a Y, you just use some factors, such as a 0.5. This value will be a little bit different for the glass composite and carbon composites. Okay, shear strength is the same, and this is the resin shear strength. Okay, resin shear strength, and you can say that this is the XM. Okay, this is the XM times about 50%. Not precisely correct, but it's not easy to measure the shear strength of a resin. Okay, well, we can use a dog-bone type test and to measure a resin strength and the stress strain curve. Typical stress strain curve is like going, and since it's a plastic, well, epoxy will just break here, and the thermoplastic will go like that, and very high failure strain. But here is the stiffness, and here is the yield strength or ultimate strength. So I will call this one is the XM. Again, the shear strength is very difficult to measure, so you can approximate like that using the von Mises failure criteria. Okay, so this is the one, and this one is the another factor you can specify. KS can be you can input the value, but you can just assume as one. Okay, and this is a last one, and longitudinal compressive strength. What it means? Longitudinal. Well, this is the fiber, and now stress is under compression this way, and sigma x, but this is a negative. Well, sigma x is a positive, then the strength will be simply x, but the compression giving us a independent properties, and this is a compressive, and this, if we look at the one fiber will subject to a compression load. But here, important point is this resin support all along the fibers, right? Imagine there is no resin. Well, this fiber will easily buckle like that, and the strength will be pretty much low. Compressive strength is not coming from material properties. Compressive is mainly from a buckling behavior or kinking behavior of fibers, which is important. Okay, it's not the material properties. Anyhow, this is the X prime, and all the X prime is affected by the resin support laterally. So this is the EM, and EM, well, there's some derivation, but here, if we have a very strong epoxy, then compressive strength is high. Well, this is not a truly accurate equation, but this is the one equation. So you can say that this is the some factors times EM. Okay, factor can be experimentally determined. Oh, there's one more. Last one is the transverse compressive Y prime strength and under compression, and the failure mainly occur in the 45 is a shear dominant, and this Y prime, you can say that XM, meaning, what is this? This is not quite true. XM is the resin tensile strength, but this one, I would say, okay, you can also introduce some factors, okay, Y prime, some factors. Well, yes, we know that prediction of the strength is not easy, okay? Prediction of a stiffness is relatively easy and straightforward, but prediction of strength using rule of mixtures, especially using this kind of simple rules, is not easy. but you can just program like that, okay? And this one, you can think that different types of a fiber arrangement. This is the procedure of analytical solutions, and this is the one equations. As you can see here, EY can be is a function of the fiber and resin, and which is different from a previous one. But this one, okay, this is the one you can use. You know, previously we used the VM, EM plus VF and EF, right? And this one is the more accurate. Okay, so well, this is the some amplification factors, which just for your reference, okay? Just for your reference. So one last comment is that in your Excel, I will cover the optimizations and 3D beam like that. We will cover next class, but in this week, I hope that you follow all the rural micromechanics, and then you do all these applied properties can be predicted from fiber, okay, can be fiber properties and resin properties. So say AS4 peak, now you can say fiber volume fraction and AS property of AS4 and property of a peak. Then following these rural mixtures, and you can get this value. Well, not as accurate as the experimental one, but it's good enough. And instead of this all this 4 property and strength property, you can use the fiber and resin properties and volume fractions. Okay. Okay. I'm sure you have a lot of questions, but sorry, no time to discuss further. And this is, if you have any question, please do not hesitate. Contact me through KakaoTalk. I will happy to answer you. Okay. So I will again assign the homework and this weekend, and also there won't be no class next week. So you have enough time to do a lot of, not a lot, but some homework, and which will be due in 2 weeks. Okay? Okay, so have a good long weekend.